tell you. Okay, you can just verbalize them?
Yeah.
Okay, go ahead.
So, use the graph of f to describe the transformation that yields the graph g.
Okay.
And then the equation is f of x equals 2/3 to the x. And then
two-thirds what?
And then that's in parentheses to the x.
To the x power?
Yes.
So there's not parentheses, it's this. Oh, it's like this. Okay.
Yeah.
Okay.
And then g of x equals 8 minus parentheses 2/3 to the x.
Okay.
And that's it.
Right. No, I get it. All right. So f of x is the parent function, right?
Yeah.
And when you have a number that is less than 1, actually I should say between 0 and 1, then it doesn't look like this. It looks like this. All depending on whether the base is greater than 1 or less than 1. And you'll get either the black line if it's greater than 1 or the red line if it's less than 1. Well, it's less than 1 here, so I'm going to erase the black line. And what we're looking at is what this function would look like. Okay, in other words, that's that function. Now let's look at this function here. Well, the easier way to look at this would be to rearrange it. So I got minus 2/3 to the x plus 8. See what I've done?
Yeah, that was kind of confusing me. And does it matter if the x is on the inside or the outside of this parentheses?
Definitely does. And excuse me, I wrote it wrong. It definitely matters, and I put it inside and it needs to be outside like that.
Yeah.
And I wrote it wrong here also. That x is outside the parentheses. The difference would be if I put it inside the parentheses, then it's going to apply only to the 2, not the 3.
Yeah.
But if I put it outside the parentheses, then it applies to everything that's inside the parentheses. So this g of x that I've written is the same as that g of x. Only it's a little bit easier now to see what 2 transformations have happened. What 2 things are different?
From the original to this one?
Yeah. In other words, what's different between that and this?
Well, it's reflected over the x and then also the y-axis.
No, just the x-axis. When the negative sign is in, okay, so the first, in other words, if I was going to plot minus 2/3 to the x, it would graph like that.
It would go through -1.
What's that?
It would go through 0, -1.
Yes. However, now I still have to add 8. What's the 8 do?
It moves it upwards 8.
Okay, so that's 0, -1. So this point's got to go up here. Doesn't change the shape, but it's now 0,7 because we had to move it up 8. And its final appearance is going to look exactly the same shape, but it's going to look like this now.
Yeah, so if I was describing that, I would say it was reflected over the y-axis.
No, over the x. It's reflected over the x-axis. Notice the black. notice the black is a vertical reflection. It is a reflection of the red, but it's a reflection over the x-axis, not the y-axis.
Yeah, I was reflecting it from if there was just one.
Here's the difference. If the minus sign,
I know what you mean.
if the minus sign is in front of the function, it's always a vertical reflection. If the minus sign is inside the reflection like that, then that would be a reflection over the y-axis.
Yeah, now I get you.
Okay. Let's take a function that's a little more evident of that. Have you had that? I'm sure you have. If I take this function here, okay, that looks like that. Well, if I put a negative sign there, that's a vertical reflection because it's outside the function. Anything that happens outside the function in the way of transformations is vertical. Anything that happens inside the function is horizontal. So if I wanted to graph that, it would just be this. But if I put it inside the function, which is to say putting it in front of the x like that, now instead of reflecting over the x-axis, it reflects over the y-axis and looks like that. The red is a horizontal reflection of the black. And that's the way you want to take all of the easiest way to deal with transformations is to separate them into 3 vertical and 3 horizontal.
Yeah.
And it's as simple as that. In other words, here, let me draw the vertical ones. If I did this, that's outside the function. That's a vertical. That's not a reflection, but it's a vertical stretch. Okay? If I wrote the function and added some number to it, well, that's a vertical shift. And if I take the function and put a negative sign in front of it, that is a vertical reflection. Vertical reflections being over the x-axis. You see why I call that a vertical reflection?
Yeah, I do.
Okay. And horizontals are f of 2x, that's inside the function. That's a horizontal stretch or shrink. Or if I had this, that's inside the function. That's a horizontal shift. And if I had f of negative x, that's inside the function. That's a horizontal reflection. So these are all vertical. These are all horizontal. And if you separate them into those 2 categories, it makes transformations a lot easier to solve and figure out and think about. And when you're doing these transformations, you always have to do the reflections first. It will make a difference sometimes. You will not necessarily end up with the correct graph if you do not do them first. If there's 2 reflections going on, like say I had a negative e to the negative x, well, you can do them in either order. But if I've got a vertical shift going on with that, then I've got to make sure that I do those reflections first. Well, my thing seems to have stopped working. Let me reopen it here. Sometimes I have to unplug my drawing tablet. Wow. Okay, it's good now. All right, so what is your other problem? What's your next one?
My next problem is f of x equals 4 minus log base 10 out in parentheses x plus 5.
Okay. What's the parent
And
function?
then we have, no, this is one of those. It says, find the domain, X intercept, and vertical asymptote.
Okay. What's the domain?
And sketch.
So hold on, let me write that. The domain, the X intercepts, and the vertical asymptote. Okay. The domain. When you talk about domain, it's really, the domain is what can X be? In other words, can X be minus 10? No, because you can only, in other words, the argument has to be greater than 0. So the way to figure out the domain is, let's take that argument, x plus 5, let it be greater than 0, and solve that inequality. That gives you x is greater than minus 5. That's the domain. Do they want it in interval notation?
Yeah, she likes it -5 to infinity.
Okay, with parentheses on both ends.
Yeah.
In other words, you got parentheses on the left side because x cannot be minus 5. Then you would be having the log of 0, and you can't take the log of 0. You can only take the log of positive numbers. So it's more restrictive than the square root function. The square root function, x couldn't be 0, but not logs. Okay. Now, how do you solve for x intercepts?
You set it equal to 0.
Yeah, x intercepts, by definition, x intercepts means y is 0. So I'm going to set this whole thing equal to 0 and then solve that equation. If I can ever get this thing to erase. All right. So if I set that equal to 0 and now solve that equation.
You would subtract the 4.
Let's keep everything positive.
And then you can subtract the 4 and cancel both negatives.
Okay. The better way I like of looking at that is, let's move the log to the right side. And then we don't have any negatives that we're dealing with at all.
Yeah.
Okay. Now, how do I solve that? How do I solve that equation?
10 to the 4th equals x plus 5.
Yeah, good. 10 to the 4th equals x plus 5. Well, 10 to the 4th is 1 with 4 zeros equals x plus 5, which means x equals
9,900. There's not any 9. Yeah.
Yeah, just subtracting 5 from both sides. So the x-intercept is 9995. Now, vertical asymptotes. Let's talk about the natural log function. If I said y equals log base 10 of x, and I wanted to graph that, it would graph like this, right? What's the vertical asymptote?
X equals 0.
Good. Now, if I say this, what's the effect of that 5? That minus 5.
It moves it all to the right 5.
Which moves the vertical asymptote 5 units to the right also. So I now have a vertical asymptote at x equal 5, and my function would look like this. Now,
Yeah.
that's basically what we have, only we had a 4 minus that. And
Yeah.
that doesn't, that 4 is a vertical shift, correct?
Yeah, I'll move it up 4.
Which does not affect the asymptotes. In other words, anything, yeah, so the vertical asymptote is still x equal 5.
Yeah, so, and then the sketch, we would also, we would reflect it over the x-axis before we moved it over.
Yes, exactly. In other words, the first step would look like that, and then I would move everything up by 4 units, and finally it would look something like that.
Yeah.
The vertical asymptotes don't change though with that vertical shift, doesn't affect it at all.
Mm-hmm.
If there was a horizontal, notice the horizontal shift did affect the vertical asymptotes. And that makes sense. It should.
Yeah.
Okay, what else you got?
Yeah. So this is solve the exponential equation ranked 3 decimal places, and the equation is e to the 2x minus 7e to the x plus 10 equals 0.
Okay. This is what I call a quadratic in disguise.
In the sky?
In disguise. Because you wouldn't immediately recognize this as a quadratic. If I gave you this, you'd say, well, that's a quadratic. I can factor that easily. Right?
Mm-hmm.
Well, notice the similarity. What really makes a quadratic is if this first term is the square of the middle term. And it is. If you square e to the x, you get e to the 2x. In other words, e to the x times e to the x is e to the 2x. So, in effect, this is a quadratic, and I can factor it exactly like I would a quadratic. And I will here, if I can erase this. Oh, man. And it factors e to the x, e to the x. That's going to give you that e to the 2x. Both signs have to be what?
Both sides have to be positive.
Negative. They both have to be the same, because that's the only way you can produce a plus on the constant.
Yeah.
But they can either be plus plus or minus minus, and you look to the middle term to get minus minus. And now factors of 10 that add to the number 7, that'd be 5 and 2.
Yeah.
There's your answer. Well, not quite, which means now we have to solve this. These two, right?
Yeah.
Okay. How do you solve this?
The first one is ln.
You take the natural log of both sides. In other words, like any algebra equation, you can do anything you want to one side as long as you do it to the other. Well, if I take ln of that side and ln of that side, the left side becomes just x. So x equals the natural log of 5. And you get that out of your calculator, round it off to however many places they said to.
Yeah.
And the bottom solution, I'm going to take the natural log of both sides. And this gives me x equals natural log of 2. So natural log of 5 and natural log of 2 are your two solutions.
Mm-hmm.
And I'm not real thrilled with the fact that she wants you to give those answers in decimal. Those should not be given in decimal.
That's what my homework book said. of
the
that.
answer really is natural log of 5 and natural log of 2. That's the answers. Those are precise. In other words, natural log of 5 is a little bit like pi. The moment you convert it to a decimal, you have approximated it. You're no longer giving the exact answer. No matter how many places you round it off to. You could round it off to 17 decimal places and you're still approximating it because it's an irrational number. It goes on forever. So the most precise way to give the answer is natural log of 5 or natural log of 2. It's like square root of 2. You don't round that off, or you don't do this anymore. You might have at one point in your algebra career, but at some point in math, they want exact answers, and that square root of 2 is the exact answer.
Yeah.
Okay? What else you got, Max? Incidentally, on that one problem,
Yeah.
remember the problem that...
Oh, yeah, the big one we did?
Yeah. Did you have to tweak that at all?
So after you gave me what you gave me,
Uh-huh.
I did to the 4 and to the F, or 1 to the 4th and 1 to the 6th, because I gave it that extra bump.
Ah, okay. So you did have to tweak it a little bit.
And also you had, on the top, you had 1 minus X.
Uh-huh.
But if that's to the 4th, that was the equivalent of just saying X minus 1.
Well, it is, isn't it? But for some reason, when I tried X minus 1 to the 4th, I didn't get the right picture. That's why I switched it. But you're right. 1 minus X to the 4th is the same as X minus 1 to the 4th.
Huh. Yeah, so and since we had to write it out, I just left it as X minus 1 because that's explained why.
Let me give you just a couple of clues as to how I came up with the answer.
Okay.
First of all, when you have this situation, remember this, when we looked at this, I said it's strange that they're not coming from opposite sides of infinity.
Yeah.
Well, the things that don't come from opposite sides of infinity are things like 1 over x squared, which looks like this.
Oh, yeah. So that was
okay. So my reasoning was that the bottom has to be a power 2 greater than the top, not 1.
Yeah.
And so that's where I decided that whatever the maximum power in the numerator was, I'm going to have 2 greater than that in the denominator. And I started playing around with that, and I eventually got a shape that gave me the proper shape. In other words, where I get the top right is there, the middle is there, and the lower left is there. And then also, there's only so many things you could tweak. You couldn't tweak everything, because if you tweaked other stuff, then you ruin the y-intercept. For the y-intercept to be 4, you could only tweak the exponent on the 2 denominators. Well, excuse me, on the denominator and the numerator. But that's how I figured it out, was when I realized that when the denominator is 2 degrees higher than the numerator, you get this situation where they both come from negative or from positive or negative infinity. But they don't come from opposite sides. In other words, 1 over x looks like this. Here the denominator is only 1 degree higher than the numerator. And they come from opposite sides on either side of the vertical asymptote. So when I saw that they're coming from the same side, I figured, well, something needs to be 2 degrees higher in the bottom. And that's where I started from. And then I just started trial and error and tweaking things and seeing if I could get the curve to come out at least looking close. In other words, having everything in the right quadrant was the first step. And then once you get that, then you can tweak. In other words, you could raise the exponent on the numerator by another factor of 2, as long as you raise the exponent on the denominator by another factor of 2. And then that gives you that little bump like that. Okay. So did you get full credit on the problem?
So I haven't, she hasn't gotten that back to us yet, those projects. We all have to write like a big write-up of it.
Okay.
But on the separate quiz that I had also that day, I got a 93 on that.
Well, good. Good for you.
Yeah, that was good.
Yeah. Okay, we just have a couple of minutes. Do you have one last problem that is a quick one?
I have one that's one of those half-lives. I don't know how quick it is.
Okay, give it to me. We'll do it quickly.
All right. The rate of exponential decay of iodine is negative 0.087. And then it asks, what is the half-life, and also determine how long it will take 100 grams to decay to 10 grams.
Okay. What's the general formula for exponential decay?
A equals C e to the kt.
And did you get it straightened out? Your teacher does not use the negative sign?
Yeah, she does not.
Okay, that's fine. I don't think it matters. I've always tried to figure out why they have the negative sign there. Okay, so if we fill in everything we know here, we know K is minus 0.087 times T, right?
Yeah, and then you can put in 1/2 and 1.
Yeah, so 1/2 P would be the material loses half of its mass. Now we have this. The P's cancel. Now we only have one variable to solve for, T. In other words, based on the rate of decay that they gave you, you're able to figure out the half-life of this material.
So, and
once you do that, once you figure out the half-life, now you're trying to solve this. 100 is going to 10. And it's e to the minus 0.087 t. And now you want to solve that for t.
Yeah.
And notice you're going to end up, there's only one variable here. To solve both of these, you got to take the natural log of both sides. To solve for the half-life and to solve for the time it takes to go from 100 grams to 10 grams.
So if you solve for the half-life, it's telling you how many years it would take for that to split in half.
Yeah, and they're two separate problems. In other words, this is not a problem where you have to solve for the half-life in order to be able to solve for this. Once they give you this rate of decay, that's all you need to know. In other words, that allows you to solve for the half-life. It also, in one step, allows you to solve for how long it would take to lose 90% of its material. And both methods are going to require you to take the natural log of both sides. The second one, the very first thing I have to do is this. Now you take the natural log of both sides, divide by that coefficient, and you solve for t.
Yeah.
All right. Max, I'm going to let you go. Glad to hear you're doing well. I'll talk to you next time.
thank you.
Bye-bye.